Hello everyone. Okay, so today we're looking at derivative at a specific point. So my first question to you is, what does the limit as h approaches 0 of the quantity x plus h squared minus x squared all over h mean? Well, it looks like the definition of derivative, right? So it is the derivative of f of x, but what is f of x? What's the function that they're plugging into? Remember, this part is f of x, and this part is f of x plus h. So all they're doing is x squared, and yes, that's the quantity x plus h squared. So here, we know that this then means the derivative of f of x when f of x is x squared. Well, what if I change this to the limit as h approaches 0 of 4 plus h quantity squared minus 16 all over h. Now notice this is a 4 because this is supposed to be x plus h quantity squared. 16 is 4 squared, isn't it? Okay, which would be f of 4 if f of x is x squared. So this is the derivative at 4 when f of x is x squared. So in this case, we plug the number 4 right into the definition of derivative in place of x, and that'll give us the derivative at 4. Okay? That's one way to find the derivative at a specific point. There is another way. So another form of the derivative, let's say we want to find the derivative at a point A. So here's A on our number line. Okay? So if this is A, then the height at A of the function would be f of A. And if this is our other x value, then the height is f of x. So the slope would be the change in y's, which would be f of x minus f of A, over the change in x, which is x minus A. Now, if we want this to be the derivative, what has to happen is we have to take the limiting value as the interval that gets smaller. Well, this time, that means that the x is approaching A, so that the derivative of f at A is the limit as x approaches A of this average rate of change formula, f of x minus f of A all over x minus A. And that, the limit of that, will give you the derivative at a specific x value. Let's look at an example. Let's let f of x be the square root of 2x. We want to find the derivative of f of x at x equals 3. So we're looking for the derivative of f at 3. So now if our definition of derivative at a point is f prime of A is the limit as x approaches A of f of x minus f of A all over x minus A, we're going to let A be 3. So f prime of 3 is the limit as x approaches 3 of f of x minus f of 3 over x minus 3. So we have the limit as x approaches 3. Now f of x is the square root of 2x minus f of 3 is the square root of 2 times 3, which is the square root of 6 over x minus 3. Now, if I try to substitute in the 3, on the bottom, I can see I'm going to get 3 minus 3, which is 0. But check the top. I'm going to have the square root of 6 minus the square root of 6. I'm getting 0 over 0, which means more work to do. This does not look like something I want to factor. So instead of factoring, let's rationalize the numerator. So to rationalize the numerator, we multiply the top and bottom by the conjugate, the square root of 2x plus radical 6. So we still have our limit as x approaches 3. Remember, since we're rationalizing the numerator, we do not distribute in the denominator. That will just make life more difficult. But in the top, the radical 2x times radical 2x is 2x. These terms here, that's going to be a radical 12x, and this is going to be a minus a radical 12x. They're going to add to 0. And then finally, a negative radical x times a positive radical x is a negative 6. Still, if I substitute, I'm still going to get 0 over 0. But that's because so far I have not been able to simplify. Well, my denominator doesn't look like it's going to get any simpler. But my numerator has a common factor of 2. And if I take out that 2, now I can see the common factor x minus 3, which will divide out. So now it's the limit as x approaches 3 of 2 over the square root of 2x plus the square root of 6. Now we can do substitution. 2 over the square root of 6 plus the square root of 6, which is 2 over 2 rad 6, but that simplifies to 1 over radical 6. So we now know that the derivative of f at 3 is 1 over radical 6. Whew, gotta love that algebra, right? It's not the calculus, it's the algebra. Now that we have the derivative, let's find the equation of the tangent line. Now remember, the line y minus y1 equals m times x minus x1. We need to know an x1, a y1, and a slope. Now the x value they gave us. However, to find the matching y value, we need to plug the x into the original function. So we need to do the square root of 2 times 3. That's just the square root of 6. Then for the slope of the tangent line is the same as the derivative at the x value, which means we just found the derivative at 3 is 1 over radical 6. So our tangent line here is y minus, our y value is radical 6, equals our slope is 1 over the square root of 6 times the quantity x minus our x value is 3. Here is our tangent line. Now we're going to graph this in the calculator. In f1 of x, we're going to put our function, the square root of 2x, and in f2 of x, we're going to graph our tangent line, 1 over the square root of 6 times x minus 3, and don't forget to add the square root of 6 to bring it to the other side. Okay, let's go to our calculator. Okay guys, so we're going to press menu. We're going to add a graph page, and in f1 we're going to put our function, which is the square root of 2x. We're going to arrow down. f2 is going to be, we use our fraction template, 1 over the square root of 6, get out of the fraction, open parentheses, x minus 3, close it, don't forget to add the radical 6 and hit enter. And we can see here we have our function in blue and our tangent line in red. And if I find the point of intersection, geometry, points and lines, intersection, hopefully, there we go, 3, that is our point of tangency at 3. Remember, we can check by going to menu, analyze, dy dx, clicking on the function, telling it we want the derivative at 3, and press enter. That gives us that derivative. Now we'd have to go to the calculator page because we said that our derivative was 1 over, so fraction 1 over the square root of 6, and we do control enter, 0.408, 0.408, so that's good. We can also menu geometry, we can points and line, choose tangent to this sideways half a parabola, hit enter to drop it. Okay, I'm going to move, oops, I have to escape out of that. Move this curve. I'm going to point at that point, control menu, coordinates and equations. So now I have the coordinate. I'm going to double click on the x value. I want the x value to be 3. This tangent line is on our red line. The next thing I want to do is I want to menu, window zoom Let's zoom in. And I'm going to show you again that when we zoom in on this point of tangency, what's happening to our differentiable function and our tangent line? They're getting closer and closer and closer until you can no longer tell the difference. That is the linearization of the function. We have zoomed in close enough that our differentiable function actually looks like the tangent to the curve. All right, just a quick reminder here of the summaries that we have. The slope of a secant line or the average rate of change, they are the same thing. We have that f of b minus f of a over b minus a formula. We also have f of x plus h minus f of x over h formula. All this is the change in y over the change in x. Next, we have the formula for the slope of the tangent line, or the definition of derivative, or the instantaneous rate of change. That is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x. Remember, that's just the limit as h approaches 0 of the average rate of change. Then we have the derivative at a point, which is the same as the slope of the tangent line at a point, which is the same as the instantaneous rate of change at a point. This is also known as the slope of a curve at a point. And we could put that up here. Slope of the curve. All of these mean the same thing. Okay? So we have two different forms of the definition of derivative. One is the general that works for all x values and gives us the rule. The other is for a specific x value, and it will give us a numerical value. Let's take a look at a couple of examples. So here we have the graph of a function f, where f of b is bigger than f of a, and we know that a is less than or equal to x is less than or equal to b. So it's all the x values between a and b we're looking at. The derivative of f exists for all x in the interval from a to b, except at x equals 0. Notice the sharp point here at 0, so there's no derivative there. For how many values of c between a and b does the limit as x approaches c of f of x minus f of c? Remember, that's the definition of derivative. That's the derivative of f at c. That's the slope of the tangent line. So they're looking for how many times will the slope of the tangent lines equal. Now this f of b minus f of a over b minus a, that's an average rate of change formula. That's just the slope of a secant. So let's start with the slope of the secant line from a to b. Let's get my handy dandy straight edge. There it is. Okay, there's my handy dandy straight edge. Now, if the slope of the tangent line is the same as the slope of the secant, then we know that these lines are parallel. Right? If the slopes are the same, then they're parallel. At how many places on this curve can you draw a tangent line that's parallel to that secant? I see 4 places where I could do that. Now you just lay your ruler on the green secant line and slide it down at the same angle and see how many times it'll touch. It's going to touch around here, around here, around here, and around here. It looks like it would have touched at 0, but we have that cusp, that sharp corner. There is no derivative there. Good. Now, number 2. Let's let y of t represent the temperature of a pie that has been removed from a 450 degree Fahrenheit oven and left to cool in a room with a temperature of 72 degrees Fahrenheit, where y is a differentiable function of t. If it's differentiable, that also means it's continuous, right? The table below shows the temperature recorded every 5 minutes. Use the data to find an approximation for the derivative of y at 18. And then explain the meaning of y prime of 18 in terms of the temperature of the pie, and show the computations that lead to your answer, and indicates units of measure. So there's a lot going on here. Now we want to approximate the derivative at time 18. The problem is, if you look at the time, 18 is not in this table, but 18 is somewhere between 15 and 20. So the best we can do is do an average rate of change around 18. So to approximate the derivative at 18, notice it's not equal, it's approximate. We're going to do an average rate of change from 15 to 20. So y of 20 minus y of 15 over 20 minus 15. So y of 20 is 257 minus y of 15 is 292 all over 20 minus 15 is 5. And if we subtract, we're going to get negative 35 over 5. Negative 35 divided by 5 is negative 7. Now the degrees on the y, the change in y, that's degrees Fahrenheit. The units on the change in time, that's minutes. So negative 7 degrees Fahrenheit per minute. Now let's interpret this. Now remember, when we interpret, we use something like the not method. We need to know the noun, we need to use the unit, and we need to make sure the time is all in that answer. Okay, so what's the time? When is this happening? Now remember, T is the time since it's been removed from the oven. So 18 minutes after the pie is removed from the oven, that's when it's happening. Now what is happening? What's y? That's measuring the temperature for the pie. The temperature is, now because of this negative, we know that it's decreasing. Is decreasing at a rate of, and now we make it positive, 7 degrees Fahrenheit per minute. And there we go, we've interpreted it. Okay, let's look at another graphing situation. For each of the functions below, we're going to sketch a possible graph of its derivative. Now remember, the derivative is the same as the slope of the curve or the slope of the tangent line. Now if you look at the first example, it's a linear function which has a constant slope. That angle is 45 degrees. That means it's going right smack in the middle of quadrant 1 and quadrant 3. That's the line y equals x. That is a line that has a slope of 1. So since the slope is 1, that means that the derivative is 1 everywhere. So we would have a horizontal line with a height of 1 as our derivative. That one's nice and easy. Okay, that one's nice and easy. Let's look at the next one. Now here, let's just look in this third quadrant. We're starting off with really small slopes, close to 0, right? But by the time we're getting close to where x is 0, we have really steep positive slopes. Okay, now this graph is always increasing, which means it always has positive slope, which means the derivative is always positive. So when we go to draw this, we're going to start off with really small positive slopes close to 0, and then they're going to start increasing and increasing and getting infinitely large. And when you look in the first quadrant, we're starting off with a really steep slope, and then we're leveling off to really small positive slopes. So this time we're starting off really steep, then we're leveling off closer to 0. So this is a good guess for our derivative. I am not looking for perfection at this point. Notice there are no numbers labeled on the x or y axis. I am not asking you for the heights. I am not asking you for actual derivatives. We're looking for general shapes, okay? So don't get too crazy yet, all right? So we've learned a lot. You learned a new definition of derivative at a specific point value, and we're going to do some more work with this soon in class. Have a great day, guys.